Welcome back. Nature in Code, we're in chapter 3, and we just learned about the important concept of the effective population size. And we also learned that the effective population size, or NE here, is actually often smaller than the actual population size, and sometimes substantially so, perhaps orders of magnitude. Now, we learned one example where that can be the case, and that's when the population goes through bottlenecks. So here's population size, here's time, and you may have, fairly constant population size, but then suddenly, for some reason, you have this complete collapse, and then the population may recover again, and later may have another collapse. But in any case, this collapse here, this bottleneck, can really substantially lower the effective population size. And why is that? Well, because we claimed at least that the effective population size is the harmonic mean. The harmonic mean of the population sizes in a given time interval. And we also learned that the harmonic mean of a list or a set of numbers, x1, x2, x3, and so on, is n. So harmonic mean is n, the number of values that you have here, divided by the sum of the inverse values. So 1 over x1 plus 1 over x2 plus 1 over x3 and so on, plus 1 over xn. And we saw as a consequence that small values can really have a very substantial impact on the harmonic mean. We then concluded by saying, well, okay, we can believe that if we want to, but it's never a bad idea to actually check and implement in code and see how this really plays out. And lucky us, we've already developed a stochastic simulation of genetic drift. So let's just go ahead and modify that and implement bottlenecks. So what I would like to do is I would like to create a situation where I have a population size n, and that is constant for some time, but then every 10th generation, say, it collapses. And then after one generation, it fully recovers, and then again, 10 generations later, or 9 rather, every 10th generation, it collapses again. So this is sort of an idealized situation. Population bottlenecks never look exactly like that, but it gives you an idea what to implement. Makes this easy to implement. And the example that I would like to develop is where n normally is 1,000 individuals, but every 10th generation, I would like n to be 10. So it's 1,000 up here, but it's 10 down here. Now, what does that mean? So the average population size here, the arithmetic mean, would just be, so the mean would just be 901. And I'm saying here approximately just because it kind of depends where you have the exact cutoffs, but I hope you get the idea. You have 9 generations of 1,000 individuals, so that's 9,000 added up, and then 1 with 10 individuals, so that's 9,010 divided by 10, that's 901. On the other hand, the harmonic mean is 92. And you can verify that yourself using the formula that we used above. But we're also going to implement it in code. But in any case, you can see here that we have a difference here of about 10, so factor 10, so an order of magnitude difference. And so, that's why this effective population size matters, because a population with an effective population size of 92 will behave from a genetic perspective substantially different than a population of size approximately 900. And if you go back to our code that we implemented, this drift code here, you can verify this yourself. Just set the population size here to 901, save it, go back to your browser and load that document. If you do that, you can see here, drift is in full force, and you're, losing quite a bit of genetic variation here. And that's approximately what it looks like. But now go back to the code and change the population to 92. Save, go back, reload. Now this looks very different, right? I mean, here, for example, we already have 3 simulations out of 10 where one of the alleles gets lost and the other goes to fixation. Here we have 2 or 3. Here we have another 2. So, this looks substantially different from the case where the population size was 901. Now the claim is that even though we might have an average population size of 901, a population with these bottlenecks will behave more like this, what you see here, rather than a population of size 901. And so I would like to implement those bottlenecks in code so that we can go ahead and test this. So let's switch over to our code. First of all, let's change n back to 1000. And now I'm going to do this in 2 steps. So the first thing I'm going to do is I'm actually going to calculate the effective population size and then plot it here in the legend. So what I would like to do is I would like to keep track of all the population sizes that we have, because population might change over time, the population size. And so once the simulation has run its course, I would like to calculate the effective population size based on all those population sizes that we had. So I need to have a way to track this. At the moment, we don't need that, and we haven't implemented that simply because we just assumed n to be constant. But now let's assume that that's not, that might change in the future. So I'm going to set up here an array that will allow me to keep track of the population sizes over time. And I'm going to call this population underscore sizes, and I'm going to initialize this to an empty array. All right, so now what I'm going to do is I am essentially going to go here to the simulation function. This is the function that gets called for once for a simulation run, and then it's basically a loop that iterates over the number of generations and calls this function next generation. So here, this is every iteration here is 1 generation. So here I'm going to push n into this array. So I'm going to say population sizes push, and then I'm going to push n in here. Now this might strike you as odd because we're not changing n, and so effectively we'll just get an array that has many times just this value of n. And this is correct right now, but we'll change that down the line. Okay, but assume now that n doesn't change. It doesn't matter. What we have after this loop has iterated is we have an array that has values in it, and those values are the population sizes over time. So what I would like to do after running the all these simulations is simply to say, well, I would like to calculate the effective population size as NE. I'm going to set up this variable, and let me make sure I define this as NE. And now I'm going to define a function first. So I would like to call a function that does that for me. I'm going to call that function effective population size. And I'm going to pass it the array. And now what I have to do is I simply have to implement this function that calculates the effective population size based on this array population sizes. Okay, let me go ahead and do that. So I'm going to define here a function I'm going to call effective population size. And it's getting an array, and I'm just going to call this parameter here, or the argument, all n's. That's just the name of the argument, so that's going to be your local variable within the function. And so here I need to essentially calculate the harmonic mean of all these n's. And so the numerator here is going to be very easy. It's just going to be the number of elements that's in this all n's. And the denominator is going to be the more tricky part, so I'm going to calculate that first. Denominator, just going to set up a variable at value 0. So basically we just learned that the denominator will be the sum of all the inverse values. So I'm going to loop through this array. So the condition will be I smaller than all n's dot length. And then of course I'll make sure I update this internal counter here. And now I'm simply denominator going to add to what I already have, denominator, the inverse of the value that I currently have in the array at this position. So this will just create the sum here of all the inverse values of the n's. And now basically I can just simply return the number of n's, so all n's length, divided by this denominator. And that might be a sort of ugly looking number with rounding errors and what have you. So I'm just going to round that to the nearest integer using this math round function that JavaScript provides. That's good enough for the purpose here. All right, so we just defined a function that takes as an argument an array of population sizes, and it will return the effective population size, the harmonic mean of all those n's. And just as a side note, you may have noticed I'm actually pushing the n's here for not only for each generation in each simulation, but of course I'm doing this over the entire set of simulations. But that is fine. It doesn't really change anything because we're keeping the population. Each simulation will be set up in the exact same way as the previous one, so this won't change. But if you were concerned about that, you could also implement, this function in a way that it calculates your effective population size for each simulation separately. So you would then rather call it here after the simulation is done, rather than down here when all the simulations have done. But again, it would just yield the exact same value. Okay, so now I would like to update this here down here. So in the legend, I want to show NE, not N, and the title here should be effective population size. I'm just going to abbreviate this so that it doesn't flow over the figure. Okay, I'm going to save this, and now I'm going to reload this. And so as you can see here, the effective population size is calculated as 1,000. If I reload this doesn't change, and this is correct. And it's correct because population size actually doesn't change. It's always 1,000, and so the harmonic mean of however many 1,000s you have will be 1,000. but the code is working. It doesn't give us any errors, and it plots the effective population size here. So in the next video, we're actually going to implement the bottlenecks. See you in the next video.